Hello everyone. Today I'll be talking about scaling pre-training to 100,000 GPUs and the challenges we encountered while doing so and the solutions we explored. My name is Saif and I'm a software engineer at Meta working on collective communications. Before we do so, let's take a look at the evolution of LLMs. LLMs are advancing rapidly across the industry, and in every generation, they are getting bigger and are getting trained on even larger dataset. For example, Llama 2 has been trained with 70 billion parameters and 2 trillion tokens on 2000 GPUs. Llama 3 has been trained on 405 billion parameters with 15 trillion total tokens and 16,000 GPUs. Llama 4 early versions were trained on 288 billion parameters, active parameters with 2 trillion total parameters, and 30 trillion tokens, and on 32,000 GPUs. So a typical training lifecycle looks like this. All the GPUs that are part of a single job, the training job spans for several months. In their lifespan, they come across several hardware failures that causes like the job to fail, and then the job would go about resuming from the checkpoint. In this example, a training job produced checkpoint every 100 steps, and it will resume from the most recent checkpoint. However, every time a job is started, it needs to go through an expensive procedure in order to start training again. And in this case, first the resources are needs to be allocated. Once the resources are allocated, a training job goes through the initialization phase where it performs collective initialization to enable communication across all the GPUs and then goes through the model loading and data check, data prefetching. And then once the initialization is complete, it begins performing the training steps. So as the job scales, overall initialization time increases. We observed collective initialization being the biggest contributor to the overall initialization time, and as it correlates to the number of participating ranks. Model loading and data prefetching mostly remain static with respect to the model sizes and data size. As we can see in this picture, we observed initialization from collective libraries to take 112 seconds at 4,000 GPUs. While at 96K GPUs, we predicted it to be 15 minutes of time alone in order to perform as part of initialization. So as we scale the job, the time to start up the job increases and the probability of failure also increases. So we expect to have one failure every 32 minutes at 100K scale and approximately 15 minutes of recovery time. So this effectively leaves us where job is training, fails, recovers for 15 minutes, train again for 15 minutes before it encounters some hardware failures and resume and repeat. This gives us an effective training time of 50%. This means the GPUs are not being utilized at all while the initialization is being carried out. Just because of one bad GPU that has caused the job to fail. So our goal is to optimize the effective training time. We explored twofold solutions where one, we go about scaling collective initialization and make sure it's optimized to reduce the initialization time. And the other one is to about fault-tolerant training paradigm that enables the job to continue training with the remaining healthy resources and only take out the bad resources when a failure occurs. First, let's take a look at collective initialization and some of the key improvements that we carried out. Collective initialization is described as creating multiple communicators. A communicator represents a set of participating rank. A default communicator represents all the GPUs that are part of a job. And that's the most expensive initialization piece. And there are communicators per parallelism with a representing subset of ranks, and they are often derived from the parent communicator with the communicator split logic. So the communicator initialization consists of these notable steps. First, it goes through a bootstrap phase where it discovers its peers and forms a ring. It uses this ring to exchange the topology data that is local to each GPU to enable everyone else to learn about the data. And once the data is disseminated, Every rank in parallel goes through topology computation, and this data facilitates the buffer allocation and channel setup for the data movements. Diving deeper into bootstrap phase, we learned that basic ring formation is estimated to be over 2 minutes at 100K. So we implemented TCP-based initialization for the ring, where each rank will set its own addresses into the TCP store, and then they will get their peers' addresses from the TCP store. The TCP store is provided from the PyTorch, and it is an existing framework that PyTorch already leverages. And we internally changed Nickel in order to leverage the TCP store and bypass and the default implementation of the ring formation. With this, at 96K scale, this gives us back 2 minutes of time frame from 132 seconds to 9 seconds with the TCP store implementation. The second notable improvement that I'd like to highlight is in altogether. Once the ring is formed, the data is exchanged using an altogether implementation over the ring. And this altogether is performed as each rank sends the data to the next rank and receives from the previous rank. And then it will do so n-1 times. And after that, it has the data of every peer. However, we introduced a bidirectional altogether, which concludes in n/2 step. In every step, a rank will send data to both of its peer on left and right and receives from both sides. So this cuts down the time in half. Now you may be wondering, why don't we do it on a collective all implementation layer in GPU? So on the CPU side, during the bootstrap phase, the data goes over TCP sessions. And most of the time, and data sizes are relatively small, and most time is spent on waiting for I/O. So we are not bandwidth bounded here, but rather we are more on the I/O bound. And thus, these improvements cuts the time by half. So with these improvements that I described and a couple more, we tested on our 4K GPU cluster, and the results were promising. We were seeing the numbers that we were expecting. However, we lacked the GPU resources for ultra large scale testing beyond 32K GPUs. GPUs are expensive and you just don't get them for free for testing, and they take time to land in your data centers. However, we wanted to be ready when the time is right and resources are available, we can initialize successfully to all the way. So in order to do so, we built an emulation framework where we mocked CUDA, which is a primary interface to talk to GPU, and IBverbs, that's a primary interface to do RDMA programming to the NIC. And with these two mocked libraries, we can compile Nickel without any changes in it, and we're able to run on the CPU server. Now, this changed the whole scaling paradigm for us. CPUs were readily available and they are pretty cheap. On the top, we packed 32 processes per node. So we just needed 3,000 CPU servers to run 96K scale run. Now we did a run and ran into a lot of surprises. I would like to highlight few. First, we learned that as we were going through initialization, an excessive amount of time was being spent just doing busy CPU cycles. And this was evident in our CPU utilization of the job in their first several minutes of time frame. We quickly did a CPU profiling, and it just pointed out like this piece of code is taking this much time. And we discovered that, oh, yes, topology processing was implemented as O(n) square. And obviously, as n grows to 100K, you are just doing 10 billion operations right there, which is several dozen seconds. On the top, we also learned socket connection errors beyond 64K scale. So our emulation runs were fine up to 32K, 64K, but when we did 96K, we learned that, oh, it was just failing with some socket errors in the TCP store. So every rank connects to TCP store. So that means TCP store has to handle 96K connections. And while digging deeper, when we know of this problem, it was occurring because a system has a 64K connection queue size, and there were silent connection reset beyond this number. So in both cases, as we saw, it was super hard to find a problem. It was just through the experiment we noted that it was much easier through the experiment to find a problem. Once we found the problem, delivering a solution was relatively straightforward. On the top, altogether that I discussed previously, you could think of, hey, you did a ring in n by 2, why don't you do tree? And yes, that's what we thought as well. And we implemented a tree solution which can conclude in log n steps as opposed to n by 2 steps. And to our surprise, it was not showing any performance improvement at a large scale. And on digging deeper, we learned that all the traffic goes through the root node, which is a funneling of traffic. And that funneling is slowed down by the excessive IO context overhead because messages are small and every send and receive is an expensive context call between the user process and kernel process. So with that, we were able to rule out a complex implementation of tree and just decided to proceed with the ring. So now I talked about optimizing collective initialization that helped us get better effective training time. Let us shed some light on an alternative approach of fault-tolerant training. So a large job trains with 100,000 GPUs and a single failure halts everything. What about if we can isolate a failure to a subset of resources in a job and while continuing the remaining resources of the job to train? So this way we don't halt everything for while there is a recovery. But before we dig deeper, let us understand parallelism setup for training. A model is sharded across all the GPUs, and we often use a 3D parallelism strategy to do so. Pipeline parallel, tensor parallel, and FSTP being the outermost. Losing even one shard means you no longer have full state to run a step. You must restart the whole thing. Now, as we are training a large model, the model is not large enough that you need 100K GPUs to shard your parameters and fit it onto it. It can often be fit to a relatively smaller group size for efficient training. We can add model replicas to scale up data parallel dimensions. As you can see in here, each replica represents a model and it's trained on a subset of data set, while other replicas are trained on a different data sets. And only added communication across the replicas is all reduced towards the end of the step. And as you can see here, this is not redefining any parallelism strategy as such, but it's rather an existing parallelism strategy that PyTorch provides out of box called HSTP, hybrid sharded data parallel. And we can leverage this replication in a classical distributed system fashion. When a replica dies, we only lose the servers of those replicas while the other replicas can continue training. So a training job looks like it's consisting of multiple task groups, each task group representing a replica of a model. And model architecture and performance requirements will determine the sizing of the task group and the number of task groups. All model shardings are localized within a task group, and we synchronize gradients across the task group using fault-tolerant all-reduce. So this is still a full sync training. So at the end of each step, all the replicas synchronize their gradients and model parameters across all the replica using fault-tolerant all-reduce. Now, as the replica goes in and out, the fault-tolerant all-reduce is to the rescue. In order to have a fault-tolerant collective, we needed to build a global coordinator, which is an external system that sits outside of the job, and every replica checks into it. And thus, it can provide a quorum view of which replicas are currently participating in a given step. And this quorum view is retrieved by all the participating ranks, and that is used to create the fault-tolerant communicator, which can resize dynamically. So when a failure occurs, you go through a shrink. During a shrink time, the current training steps will result into the collective timeout errors. And it's bounded by the timeout, which is often a minute or two. After the timeout, a quorum is reformed and ranks will know of the reduced set of replicas that are part of the subsequent step. And given that step failed, it has to be retried. So you have to pay a cost for it. And then the remaining n-1 replica will resume training and will not wait for the replica that's down. So, and in the grow side, when replica joins, there has to be a quorum reformation. Once the quorum is reformed, all the other replica will halt for a while until the new replica that catches up the model and optimizer checkpoints from the healthy replicas. And it will load its data checkpoint from the shared file system. And once this is done, it will start training. In our internal testing, the shrink and grow phases can effectively be finished within 4 minutes of time frame. So it halts an overload training for a very reduced amount of time. And the down replica can take several minutes to recover, but that cost gets amortized as n-1 replica continues to train. So to recap, for large-scale training, both of these approaches improved an effective training time to a significant degree, up to 90%. Optimizing collective initialization has directly improved the recovery time of the job, while fault-tolerant training, which is a new paradigm that improves the effective training time by allowing the resources to work in parallel while the failed resource recovers. To recap, key takeaways from the talk: hardware failures are inevitable, and at a large scale, they are very frequent and very severe, and it severely affects the effective training time. Recovering faster is the key to leverage GPU resources effectively. We don't want our GPUs to sit idle and want them to be computing as much of the time as possible. Novel approaches such as emulated framework helped us overcome the GPU resource limitation and also solve problems at scale and validate our solutions. Fast init fixes that I described are upstream to Nickel, so they are available to a broader community to benefit from them. And fault-tolerant training has proved to be practical, and sometimes we have to just rethink our approach to the training paradigms. Though we took big leaps in scaling training, we have a long way to go. For Llama 3, we thought we are done for life at 16K GPUs. That's the ceiling that it would be good enough for the future models that we need to train, but we were wrong. Scaling laws continue to challenge us and to even innovate. Fault-tolerant training is emerging. Both training paradigm and associated collective implementations are evolving rapidly, and there are many opens here for us to navigate. With this, I'll conclude my talk. Thank you all for listening.